So when you look up at a really pristine dark night sky, your brain is basically falling for one of the oldest optical illusions in the
Oh,
universe.
absolutely. We're wired for it.
Right, because our eyes are just immediately drawn to those brilliant, piercing dots of starlight. And since those stars are so overwhelmingly bright, our brains just automatically fill in all the spaces between them as this total void. Just vast, inky, empty black gaps.
Yeah, we just assume there's nothing there.
Exactly.
Yeah.
But the central premise of our deep dive today, based on some really fascinating source material on astrophysics, is that this intuitive picture is, well, it's almost completely wrong.
It really requires a total rewiring of how you visualize the galaxy.
Yeah. So today, our mission is to shift our focus entirely away from the glowing stars. We're going to uncover this incredibly complex, invisible drama happening in the exact spaces we assumed were empty. This sprawling ecosystem that astronomers call the interstellar medium.
And it's such a great topic because that supposed empty space is actually this dynamic, highly structured soup of gas and dust. I mean, it's not just a boring black backdrop.
Right.
It is the raw material for stellar birth. It's the sprawling graveyard for dead stars, and it's basically the main character in the galaxy's ongoing story.
Okay, but to really grasp this, we have to kind of unpack a weird paradox about just how thin this soup actually is, because it really challenges our basic definition of a vacuum.
It does, yeah.
Like right now in the room you're sitting in listening to this, you are surrounded by roughly 100 billion molecules per cubic meter.
Which is a very dense, chaotic swarm of air.
Right. But if you transport yourself to an average patch of the interstellar medium, you're looking at what, maybe one single atom per cubic centimeter?
Sometimes even less, which is an emptiness that completely exceeds the most advanced laboratory-grade vacuum chambers we can build here on Earth. Yeah, inside our most pristine terrestrial vacuums, there are still thousands of molecules pinging around in that same cubic centimeter. Out between the stars, the density drops by several orders of magnitude.
Okay, so let me push back on this a bit for you listening. Because if the interstellar medium is literally a harder vacuum than a pristine physics lab vacuum chamber on Earth, calling it a soup or an ecosystem feels almost counterintuitive.
I can totally see why you'd say that.
Like, why doesn't that just mean space is, for all practical purposes, empty?
Well, the resolution to that paradox really comes down to the sheer staggering scale of the universe.
Okay.
Yes, the gas is extraordinarily dilute on a local level, but when you take that ultra-hard vacuum and you spread it across trillions of kilometers in every possible direction, all that mass aggregates to a monumental degree.
So it adds up.
Exactly. Thinness multiplied by vastness generates enormous substance. When you tally up all those single atoms per cubic centimeter across the entire Milky Way, it accounts for anywhere from 10 to 15% of all the ordinary matter in the entire galactic disk.
10 to 15%. That's a massive fraction just floating around out there in the dark.
It is a massive reservoir of material just stretched to its absolute physical limit.
Which naturally makes you wonder, like, what exactly is floating around in there? Because I know it's not a uniform fog.
No, not at all. By mass, it is overwhelmingly hydrogen, about 74%. Hydrogen is, the simplest, lightest element from the Big Bang.
Right, the basic building block.
Yeah. And then you have helium making up about 24%.
Okay.
But then there's this remaining tiny fraction, often just 1 or 2%, which consists of heavier elements, or what astronomers confusingly just call metals, along with solid interstellar dust.
Let's definitely clarify the dust part. Because when you hear the word dust, you naturally think of like the lint and skin cells drifting through a sunbeam in your living room.
Oh, sure, yeah. Earth dust is mostly biological.
It's exactly. But interstellar dust is entirely different, right? We're talking about microscopic, solid grains of carbon and silicate minerals. Basically, tiny specks of soot and rock, often smaller than a speck of smoke.
Yeah, they're incredibly tiny. And this mixture of gas and solid grains isn't just sitting statically in the dark. The interstellar medium actually has intense space weather.
Space weather. I love that term.
It's highly turbulent. It's fractured into distinct phases based on some really extreme variations in temperature and density. You have coronal gas pockets that are scorching hot, warm atomic clouds, and then these freezing cold molecular regions.
See, okay, let's talk about the physics of that extreme heat, because I feel like this detail in the source material really trips people up.
The million-degree gas.
Yes. There are pockets where the gas is blasted to over 1,000,000 degrees by dead stars, but it's basically a vacuum. So if you were in a spacesuit floating through a 1,000,000-degree gas cloud, You wouldn't vaporize.
No, you would actually freeze to death.
Wait, really? How can something be a million degrees but you freeze?
Well, it comes down to the difference between kinetic temperature and thermal heat transfer. In physics, temperature is really just a measurement of how fast the particles are moving.
Right.
So when a dead star like a supernova explodes, the shock wave slams into that very thin hydrogen and accelerates those few atoms to unbelievable speeds. Because they are moving so fast, their temperature is technically a million degrees.
But heat transfer, like actually feeling hot,
Yeah.
requires collisions, right?
Precisely. If you put your hand in a hot oven on Earth, billions of dense air molecules are instantly smashing into your skin, transferring all that kinetic energy.
Right. It's dense.
Yeah. But in that million-degree coronal gas in space, there are so few atoms around that the rate of collisions with your spacesuit would be virtually zero.
Oh, wow.
The particles are moving incredibly fast, but there just isn't enough mass to transfer any real heat to you, so it would feel incredibly cold.
That is so counterintuitive, but it makes perfect sense.
Yeah.
But, while those hot, fast-moving particles are super fascinating, the most important work in the galaxy actually happens in the exact opposite conditions.
Yes, the cold pockets.
Right. The vital mechanisms of the galaxy rely on this gas cooling down, slowing down, and clumping together into visible structures called nebulae.
Exactly. When the gas cools, its internal pressure drops. In the warmer regions, the particles are bouncing around so fast they resist the inward pull of gravity. But in the densest, most frigid pockets where temperatures drop to just like 10 or 20 degrees above absolute zero, that resistance fades.
And these specific cold pockets are the molecular clouds, right?
Yeah, they're called molecular clouds because it's finally calm and cold enough for individual hydrogen atoms to actually pair up and bond into molecular hydrogen, or H2.
And this is where gravity really starts to win the tug of war against the gas trying to spread out.
Exactly. It crosses a threshold called the Jeans mass, and the cloud starts collapsing under its own immense weight. It fragments into these smaller, really dense cores.
And here is where the source material had an analogy I absolutely loved. Because as these clumps shrink under their own weight, they pull in material and they start spinning faster and heating up, which is exactly like an ice skater pulling their arms in during a spin.
It is the exact same physics, conservation of angular momentum.
Right.
As that material falls inward, any tiny bit of rotation gets wildly amplified. The core spins faster, it flattens into a disk, and the friction and gravitational compression at the center cause the temperature to just skyrocket.
Until it hits that ultimate threshold, right?
Yes. The heat and pressure become so extreme that the hydrogen nuclei are literally forced together. They fuse into helium, and that releases a massive burst of energy.
And boom, a new star is turned on.
Exactly. That fusion ignition is stellar birth. And because these molecular clouds are so huge, they don't just make one star. They trigger massive bursts of star formation, creating hundreds or thousands of stars all at once.
Like the Orion Nebula, which you can even see with the naked eye.
Yeah, Orion is a perfect example of an emission nebula. The crazy, intense ultraviolet radiation from those hot newborn stars strips the electrons from the leftover hydrogen gas around them.
And that makes it glow from within.
Right, it basically fluoresces brightly in the night sky. But you also have dark nebulae, like the Coal Sack near the Southern Cross, where the dust is just so dense it acts like a silhouette, completely blocking the light from stars behind it.
Okay, so the interstellar medium is essentially the galaxy's giant fuel tank. Without it, the galaxy just ages and goes quiet. But if it was just a one-way trip, a one-way fuel tank, the Milky Way would have run out of gas billions of years ago.
Oh, entirely. The universe would be completely dark by now.
So it's got to be a two-way street.
It is. The interstellar medium is a highly efficient recycling bin. Stars don't just hoard their mass forever. Sun-like stars will gently puff off their outer layers as they age, returning a lot of gas. And massive stars, well, they end their lives in catastrophic supernovae that violently blast their material back into the void.
And the really crucial part is that the material they return is not the same as the material they started with.
No, it is chemically transformed.
Because inside the star, it's basically a giant nuclear forge. It spends its whole life crushing lighter elements into heavier ones, hydrogen into helium, helium into carbon, oxygen, all the way up to iron.
And iron is where the star hits a wall.
Right, because fusing iron takes more energy than it gives off.
Exactly. The outward pressure stops, gravity instantly wins, the core collapses, and the rebound triggers the supernova blast.
And this is where it gets really interesting for you listening right now, because that supernova blast has so much kinetic force and heat that it forges even heavier elements, gold, platinum, uranium, and flings them all out at tremendous speed.
Seeding the dilute gas clouds with all this incredibly rich, complex material.
Right. And this isn't just poetry. The iron in your blood right now, the calcium in your bones, the rock under your feet, literally all of it was forged in the core of a long-dead star. It was flung out into the interstellar medium, swept up into a cold molecular cloud, and eventually built our sun and the Earth.
You are quite literally made of recycled stardust.
It just bridges that gap between abstract astrophysics and human biology so perfectly. But okay, if all these elements and tiny dust grains are out there building solar systems, how do astronomers actually map them? Because we said earlier, they're mostly invisible and incredibly spread out.
It's a huge challenge. Astrophysicists have to rely on some really clever observational tricks. One of the main ways is observing how this dust alters the light of distant stars. We call it extinction, which just means the dust grains physically block and scatter the light, making the star look a lot dimmer than it actually is.
But it doesn't block all light equally.
Exactly. There's a phenomenon called interstellar reddening. Those tiny dust grains are perfectly sized to block short wavelength blue light, but they let the longer wavelength red light pass right through.
So wait, this is exactly the same underlying physics as a sunset here on Earth, isn't it?
It is the exact same mechanism, Rayleigh scattering.
Yeah, because when the sun is setting, the light passes through a thicker slice of Earth's atmosphere. The air and dust scatter all the blue light away, leaving only the red and orange to reach our eyes. But in space, it's happening over trillions of kilometers.
Yeah, and astronomers take this annoying interference and use it to their advantage.
How so?
Well, they look at star clusters where they know what the true color and brightness of the star should be. Then they measure how dimmed and reddened the light actually is when it reaches our telescopes. By working backward, they can map out the 3D structure and density of those invisible dust clouds.
That is so clever, but that only covers the dust. How do they see the cold hydrogen gas itself? Because that doesn't emit visible light, right?
Right, for the cold gas, they have to shift out of visible light completely and use radio telescopes. And they rely on this beautiful little quirk of quantum mechanics called the 21-centimeter emission line.
Okay, lay this quantum quirk on us.
So in a cold, dark cloud of atomic hydrogen, you just have a single proton and a single electron. Both particles have a quantum property called spin, which creates a tiny magnetic field. Usually, they are aligned parallel to each other.
Which is a slightly higher energy state.
Exactly. But as we know, nature always wants to be in the lowest possible energy state. So
Right.
very rarely, like once every few million years for a given atom, the electron will spontaneously flip its spin to be opposite to the proton. And when it drops down to that lower energy state, it shoots out a faint radio photon with a wavelength of exactly 21 centimeters.
But wait, if it only happens once every few million years for one atom, how on earth do we detect it? That sounds like nothing.
It does sound like nothing. But you have to remember the vast scale we talked about earlier, trillions of miles of dilute gas. So across that immense volume, there are constantly enough atoms doing this little quantum flip at any given millisecond to produce this steady, faint radio hum.
So they just tune their radio telescopes to 21 centimeters and listen to the hum to map the atomic hydrogen.
Exactly. But of course, there's a catch.
There's always a catch in astrophysics.
Naturally, that technique completely fails when you look at the really dense, cold molecular clouds where stars are actually born.
Oh, because the hydrogen atoms have bonded together into H2 molecules.
Yes. A hydrogen molecule is perfectly symmetrical. It doesn't have a permanent dipole moment, which means it can't emit those radio signals at those frigid temperatures. It just goes completely dark.
So you have these massive critical clouds that are totally invisible. How do they find them?
They use tracer molecules. They basically look for a stand-in. And the best one is carbon monoxide, or CO.
Why carbon monoxide?
Because it's an asymmetrical molecule, one carbon, one oxygen. It has a permanent dipole. So even in the freezing cold, if it bumps into anything, it easily gets excited and emits a very bright detectable radio signal.
So they basically map the glowing carbon monoxide and just safely assume the invisible molecular hydrogen is right there with it.
Precisely.
Okay, so having mapped all of this out, the reddened starlight, the 21-centimeter flips, the carbon monoxide tracers, astronomers realized something highly specific and frankly a little ironic about where our own solar system is located in this cosmic fog.
Yes, the local bubble.
Right, explain the local bubble.
So we aren't actually drifting through an average patch of the interstellar medium right now. Our sun is currently cruising through a massive, sparse, hot cavity called the local bubble.
And this cavity was basically carved out millions of years ago by ancient supernovae, right?
Yeah, a cluster of exploding stars acted like a cosmic snowplow, just sweeping all the dense gas and dust outward and leaving behind this cleared-out void.
And plus, our sun has its own magnetic bubble, the heliosphere, which pushes outward and shields our planets from even more of whatever interstellar material is left.
Exactly. We are heavily shielded.
So the irony for you listening is that space feels so empty and abstract to us with these crystal clear views of distant galaxies, specifically because we are basically coasting through a cleared out cosmic cul-de-sac.
It's a huge observational bias.
If we lived somewhere else in the galaxy, like inside a dense molecular cloud, the night sky would look totally different. The dust would block the stars. You'd see dark lanes of soot everywhere. Our whole philosophy of a vast, transparent universe is totally dependent on this one little clear patch we happen to be in.
It really is. And if you zoom out to the whole galaxy, you see that this whole ecosystem is shaped by even more invisible forces. It's not just gravity and supernovae.
What else is at play?
Well, there are weak magnetic fields threading through the dust, and cosmic rays, which are basically protons moving at near light speed.
Right.
These forces actually push and organize the interstellar medium, compressing it into those massive, sweeping spiral arms that give the Milky Way its shape. And I should add, this isn't a closed textbook. Exactly how these clouds collapse or how dust grains grow in the dark are huge, active mysteries that keep astronomers busy today.
It's just so dynamic. But as we wrap up, we need to bring it all back to that recycling cycle.
Right.
Because we said the interstellar medium is a two-way street, right? The fuel tank. Stars are born, they die, they return enriched gas to the void.
Yes, but it is a lossy process.
Right, it's not a perfect one-to-one exchange.
Not at all, because every time a star dies, it leaves a dense core behind a white dwarf, a neutron star, or a black hole. And the mass locked inside those remnants is permanently removed from the ecosystem. It can never be used to build a new star.
Wow. So every star that forms permanently locks away some of that gas.
Yes.
Which means eventually, billions and billions of years from now, the fuel will just run out.
It has to. The gas reserves will thin out past the point of no return, star formation will completely halt, and the Milky Way will just enter this fading twilight.
It just fundamentally changes how you look at the sky. So I want to leave you with one final thought to ponder. The next time you look up at a clear night sky, try to hold both realities in your head. Those bright dots aren't permanent, and the black gaps between them aren't empty.
They are brimming with glowing hydrogen and dark soot.
Exactly. They are the recycled ashes of ancient stars waiting to be reborn. But knowing that the fuel is finite, what will the universe look like in the deep future when the last star finally dies out and the night sky is finally truly nothing but empty gaps? Something to think about the next time you're stargazing.